Hello, I'm Adele, and I'm going to talk to you about our work on contourite drift deposits of southwest Ireland and what they can tell us about the last 85,000 years of polar front migrations, warm current variability, and ice rafting in this area. This front cover photo is of the thermohaline circulation, which is both driven by climate and drives climate in this region. And you will see more about the connection it has to my studies very soon. This is the North Atlantic oceanography. And this, as you can see, several currents. These are indicated by the red arrows. This arrow here points to my study sites, which is influenced particularly by two contourite currents, which is currents that follow the contours of the continents. These two contourites it is impacted by is the Eastern North Atlantic central waters and the Mediterranean outflow waters, but it's also influenced by the North Atlantic currents, which travels west to east across the North Atlantic Ocean. Another thing I want to point out in this map is the temperature gradients of the sea surface temperature. Most importantly, the Arctic or polar front, which marks at about 7.5, 8 degrees Celsius. My study site, as I pointed out in the previous map, is just south of Ireland. It is site U1318, which is an IOGP site from Expedition 307. I will be comparing a lot of my data to a site called MD012461 and data produced by Adele. Here's a bit of a different way of looking at the North Atlantic. This map is showing ice rafting paths or iceberg paths in the North Atlantic Ocean. This is because Heinrich events are mass discharge event of ice from the Laurentide ice sheet. These events happen about every 7,000 years since MIS5, that is about 130,000 years ago. And as you can see, the main path of these icebergs from the Laurentide ice sheet is through this belt in the middle of the North Atlantic and straight towards site U1318 from Expedition 307 and towards the UK, which means we can record these events in the sediments as they drop off drop stones from the icebergs and into the deep sea sediments. I would also like to draw your eyes through the British-Irish ice sheet. The full extent of this ice sheet is not known, particularly not in the most recent time of the southern age of the ice sheet. So one of the aims of my project is to try to constrain that. So we started with looking at the sediment cores, which I have logged here, where the lighter color is the muds and the darker colors are medium grain sands. Most of the sands have erosional bases. Drop stones are more common at the base of these sands, and shell fragments are common as well. This photo here is from about 15 meters in the core, and you can see that relation with the erosional base to the muds, and there's a couple of drop stones in there as well, and similarly here at about 25 meters depth. These sand layers have been interpreted as contourite deposits. Next thing we did was studying the foraminiferal assemblages, which I here has split into temperature-defined water bodies. Most importantly is Neoglypocardina pachyderma. That is because pachyderma, when the foraminiferal assemblage is more than 80% pachydermis, you are in polar waters. So if you see this line I just added, every peak that is to the right of that line indicates polar water temperatures at site U1318b. And as you can see, there's several of those periods. The other thing to highlight here is that the North Atlantic current species, the ones all the way on the right in green, are pretty much inverse the pattern of pachydermis, which means when the pachydermis disappear, we get an influx of warmer water taxa in these North Atlantic current species. The same with the subtropical taxa, they are only present when there's less of the pachyderma, and vice versa. So here's a photo which shows the differences here. Less diversity is generally colder water, more diversity is generally warmer water. To make an age model for the site, I started out with stratigraphic correlation to site MD012461. This data here is by Peck et al. And as you can see, there's several correlation points throughout the cause. These are mainly based on magnetic susceptibility, but also on the percentage of neoglybulochondrial pachyderma, lithic granule or ice rafter debris. I also use some XRF data and downhole logs. And from that, I was able to produce an age depth curve, which you can see here, and the table of which data points I pointed out. And as you can see in the age depth curve, the sedimentation rate slows down significantly during some periods, which then actually correlates to the periods of more present pachyderma, i.e. colder water. So I tried to collect these different data into categories, and here is category called current activity proxies. So on the left here is sea surface temperatures in degrees Celsius calculated from the abundance of pachyderma for foraminiferous species. So again, we see this blue line, the solid line on the left. That indicates where it's 80% or more pachyderma, which is at about is between 7 and 8 degrees Celsius. The dashed line on the right in the same graph is the current or present mean annual sea surface temperature in porcupine seabed, which is at about 10.5 degrees. What is worth highlighting here is the relation again between higher sea surface temperature and more common subtropical taxa and lower sea surface temperature and less subtropical taxa. And then the simplified SED log, you can actually see these sand layers, which always correlate to these warmer periods with more subtropical taxa. So from this, we've been able to interpret several periods with increased current activity, and that's what I've highlighted with these arrows. These higher current activity periods occur only during warm periods, whereas during the cold periods, there seemed to be lower current activity. So next thing I wanted to look at was the ice sheet. So here's my ice sheet proxies from planktic foraminifera and ice rafter debris, which is counted from the sediment. And from these, we can see that there's several periods where there's increased amount of ice rafter debris. There's increased both physically counted and in the XRF data here, terrestrial input. And these generally correlate with the colder periods or periods of melting immediately following cold periods. So here is 3 periods highlighted where there's increased ice rafting and likely increased extent of the ice sheet. This period here I have interpreted to be the period with the largest ice sheet extent. As you can see, there's a significantly higher proportion of ice rafted debris, a source from the British Irish ice sheet. And that actually correlates to the last glacial maximum. And then here, there's a rapid drop-off in the amount of ice rafted debris from the British Irish ice sheet. And we, at the same time, see an increase in sea surface temperature, which could indicate the retreat of the British Irish ice sheet following the last glacial maximum. So I tried to summarize these data into some more digestible cartoons. Here I'm showing the current state of the porcupine seabed, but also during the warm periods. So you see there's active contourite currents. And then when we get into cold periods, these contourite currents shut down. You get a present ice sheet and the sea level decreases, and you have a background water body called the Upper North Atlantic Deep Water. And then there is a couple of periods where the contourite is somewhat active, but not much, more so in deeper water than shallow water. But the ice sheet is likely still present. I'm very happy to answer questions about this if you have more. To summarize this in a map, we have active contourites during warm periods, and during cold period, you have an extensive British Irish ice sheet. So to conclude that, I will leave you to read this on your own if you feel like it. And thank you very much. Here's some of the references I've used as well.